All right. So I'm going to start with a quick review of chapter 4, which is the chapter that we are studying. And what is it that we are doing in chapter 4? We were trying to solve the time-dependent Schrödinger's equation. But remember, this is now in 3 dimensions. So on this side here, we had the Laplacian. Yeah? And then the potential. Okay. Just as we used to do since chapter 2, we said if this potential, which is now dependent on 3 coordinates, does not depend on time, so that's the assumption that we are doing since chapter 2, then we can split this equation in 2 parts. One part that depends only on time, and this one is easy to solve, is the one that gives us the exponential with the energy and the time. The other part is the time-dependent Schrödinger's equation. I'm going to write it here. Now this psi depends only on, psi depends only on x, y, and z. Then we have the potential and this whole thing, energy, and the wave function. Remember that this Laplacian is the derivative, the second order derivative is in x, in y, and in z. Okay, but we can write this whole thing also using spherical coordinates. Okay, so we can use spherical coordinates, and we said, if we use spherical coordinates and this potential, which would then depend on r, theta, and phi, if this potential does not depend on the angles, theta and phi, depends only on the distance, and this distance here is the distance from the origin. If it depends only on the distance, this is what we call central potential. And again, we are going to be able, And again, we are going to be able to split now using a separation variable, now to split this other equation. In what? In a part that depends only on r, and we were able to find the part of the wave function that depends only on r, and another part that depends on the angles. Well, this part that depends on the angles, again, we split in 2 parts. One that depended only on theta, the other one that depended only on phi. The one that depended only on phi was easy to solve. It was again an exponential, I, m, and phi. The one that depended on theta, well, we didn't really solve. We just said that the solution was this PLM of cosine of theta, which is what we call the associated Legendre's functions. Okay? We just gave this to you. Okay. This function R that we found here is specific to the potential that we used, which was the potential for the hydrogen atom. This solution here, the part that depends on angles, which we said we wrote with this y, no? This part that depends on the angles, which is some normalization constant, that PLM that we wrote there, and that exponential in phi. This part here is general. Any central potential will have this solution. And how do we call this solution? The spherical harmonics. Okay. Let me remind you, that's why I have it, the screen split, of the equation that we obtained for this guy, because we are going to see this equation again showing up today. Yeah, so you can see. So the equation that we had was something like this, okay, involving these derivatives in sine and phi, and this L plus 1 is the eigenvalue of the equation. So this is the equation that we had, was equation 4.18. You can come back to your book to see. Okay, so this was the equation that gave us this spherical harmonics, and we are going to see it again. Okay, some details here. This normalization constant, we have an equation for that, but remember, whenever we're dealing with spherical coordinates, careful with the integrals. We have 3 integrals, of course, but we have the integral in R, where R goes from 0 to infinity. We have the integral in theta, and then it's sine of theta, theta, where this theta goes from 0 to 2 pi, and the integral in phi. The integral in phi that goes from 0 to pi. So careful with that. Okay, someone else. Very well. Another detail, this solution here, I expect you to know, okay, those steps and how to find this solution. This solution, these R here, let's just remind ourselves, these are dependent on N. N is the principal quantum number. N is associated with the energy of the electron that we are studying in the hydrogen atom. So depends on N, depends on L. And this had, well, it was a long expression. It has a rho, where we said that this rho was kappa R. This kappa depends on energy. And it also had a V dependent on this rho. And to obtain this V, we had a recursion form. Okay, so be sure you know how to play with these things. We also said that this V is associated with another function that people have studied, and there is an equation for this one, which is called the associated Laguerre. All these French mathematicians, polynomials. No? Very well. So this is a quick review. Now I come with the topic of last class. Last class, we started talking about angular momentum. Okay, why? Because, and this is what we are going to see today, those spherical harmonics, they are the eigenfunctions of angular momentum. Of which one? Of the total angular momentum. Okay. More people. And this is what we are going to see today. Okay, but let's start by talking about angular momentum. In classical mechanics, you know very well what is the angular momentum. It's the cross product between R and the linear momentum. And so you can find each one of the components using this expression. And so how we do that? Cross product, we have the R, so the components X, Y, and Z, and the P, the components PX, PY, and PZ. And so we can find each one of the components. For example, LX, what is LX? I go with this diagonal, so it's YPZ minus, if you want to fill it up here to guide you, minus this diagonal, so minus ZPY. And you can do the same to find LY and to find LZ. Okay, so you have that. We already talked about this. Well, this is classical mechanics. What changes in quantum mechanics? Oh, these components are now operators. So everywhere here, we are talking about operators. So let's pick the LX as an example. What is the operator momentum? We already know, but now we are talking about the operator momentum in each direction. We are playing with a problem that is 3-dimensional. So the PX is H bar I derivative in X. Okay, so same thing for Y, same thing for Z. So if I'm going to write this LX, it's going to be H bar over I, and then we have Y, the derivative in Z, and we have Z and the derivative in Y. Okay, same thing for the other guys, Y and Z. And then playing with that, and this is something that is important for you to know, okay, or these commutators between these operators. Playing with that, so be sure you know how to solve that. We found out that none of these pairs commute. So none of them commute. It's always different from 0. And it's even easy to find what is the relation from this commutator. We use this cyclic relationship. So if I'm doing the commutator between X and Y, the commutator between X and Y will be the LZ with like this, I, H bar, and the LZ. But be sure you know how to show that, okay? If I'm going to do the commutator between LY and LZ, so it's always cyclic like that, no? So if I'm going to do the commutator between Y and Z, this is going to be I, H bar, LX. And so on. And we can do between Z and X. Well, let's write it there. Between Z and X is the L1. Okay, so they do not commute, and this is very important. Why? The fact that they do not commute, the fact that they are incompatible, means that I cannot measure both at the same time with absolute precision. Now, there is uncertainty between them. So we have the uncertainty principle between X and Y, oops, Ly, given by, so this product between the variance of these two has to be larger. We cannot measure them with absolute precision, has to be larger of what? This is the relationship for the uncertainty principle. No? The commutator between Lx and Ly. That's why we cannot measure the two together because they do not commute. The expectation value of this commutator divided by 2i, all that squared. Okay, so let me show to you. So for those who are following the book, where I am. Okay, so okay, here. Almost here, yeah? So what I wrote to you is this part. You see that this is the commutator between Lx and Ly. Yeah? And so we solve this commutator is the I, H bar, LZ. And so this is the relationship. Yeah? It has to be larger than this value. Very good. In addition to this, X, Y, and Z, we also talked about the sum of the total angular momentum, the L square. The L square is Lx square plus Ly square plus Lz square. This is the total. This one, yes, this one commutes. So the L square, and you can check, the L square commutes with Lx, commutes with Ly, commutes with Lz. So what we decided to do is we picked L square and LZ, since they commute, since they are compatible, they share the same eigenfunction. Okay, so we don't know yet what this eigenfunction is. I'm going to say that it's F, and it's the same for both because they commute. And well, the eigenvalues can be different. We don't know yet what the eigenvalues are. We call it lambda for L square and me for LZ. Okay, what we are going to do is we are going to try to find these eigenvalues today. Okay, the lambda and the me. We also introduced some new operators that we call L plus and the L minus. The L plus was Lx plus I Ly, so it's just a definition. Okay, and L minus is the same thing with a minus sign. Why this is important? Because we said if F is an eigenfunction of L square and LZ, then this new function L plus applied on F, this new function is also an eigenfunction, okay? And we showed that this new function, this L plus on F, this new function is still an eigenfunction of L square with the same eigenvalue. How about the LZ? It's still, no, this new function L plus on F is still an eigenfunction of LZ, but now something changed, and we showed that last class, and this is important for you to know how to show, okay? The eigenvalue changed, became me, plus H bar. So this is the new eigenvalue. And it became plus, so that's why we say that this L plus here is a raising operator, very similar to the A plus that we deal when we are doing the harmonic oscillator. Now, if we play with the L minus is also, not L minus on F, is again an eigenfunction of L squared with the same eigenvalue. This does not change. But on the case of the LZ, it's again an eigenfunction, but the eigenvalue changes, decreases, and that's why we said that this L minus here was a lowering operator, just as the A minus that we had with the harmonic oscillators. Okay, so as we said, today we are going to try to find these eigenvalues. Okay. At the end of the class, we said, well, I start with some function f with some eigenvalue, and every time I apply the L plus, this is going to increase. No? I apply L plus, and this is increasing. Well, it cannot go on forever. It has to stop. Why? I cannot get here a value that is larger than the eigenvalue for the L square. Okay, what I'm saying is I cannot get an eigenvalue for the LZ, which is a component of the L square, that is larger than, which is a component of the angular momentum. It cannot be larger than the eigenvalue for the total angular momentum. So there should be a point, we are increasing, that we reach the largest eigenvalue and the corresponding top eigenfunction. If I then apply the L plus on this top one, this should then be 0. I stop the process. The same thing if I'm going down, if I'm applying the L minus, there should be a point where this process stops. So this is what we need to use now to find the eigenvalues. Define the eigenvalues that we call lambda and that we call mi. So this is going to help us finding them. Okay, so how are we going to do that? If you have questions, please let me know, okay? So up to this point, Kimani arrived at the right time, no? Because up to this point we had already talked, but it was long ago, before the holiday. Okay, so what are we going to do now to find these eigenvalues? Now I'm going to come with a good idea. It's a sort of a trick. What do I mean by that? I know that L plus acting on F top, no, the top one should be just a 0. So I'm going to have a look at the product of these two commutators. Oh, sorry, the product of these two operators, L minus and L plus. I want to see who okay, there is someone else coming. All right. So I'm going to look at this product. Why? Well, what is Lx? Well, what is L minus is Lx minus ILy, and L plus Lx plus ILy. Okay, so I can rewrite this as L squared. Then this one with this one is I Lx Ly. This one with this one is minus I Ly Lx. And the last term is going to be L squared. Okay, so we don't know yet where we are headed. No? So then we have, I'm going to rewrite the thing like this. Lx squared plus Ly squared. I'm going to add Lz squared and subtract, so I'm not doing anything. And this part here, I can write it like this. It's I, Lx, Ly, minus Ly and x. I can write like this. Okay? So this is an important trick. Well, what is this whole thing here is the L squared. So then I have, and what is this whole thing is I H bar LZ. So I found a way to write this product calculate L minus L plus, which is L square minus LZ square. Now, I and I gives me minus H bar LZ. So why did we do all that? Because I found a new way to write this L square. I can say that L square is equal to LZ square minus H bar LZ, minus, no, plus, no, it pass to the other side. And then plus L minus L plus. Okay. So this was the purpose of playing with this product. Now, why? Look at this. We are after the eigenvalues. No? We are after the lambda and the mean. So what I'm going to do is, well, I don't know yet what this mean is. I'm going to say that the LZ acting on the top one, I don't know what it is, but I'm going to write it like this, H bar L F top. This is just for convenience. I don't know yet what this L is. Okay, I just know that how do I got there? I went me plus H bar plus H bar plus H bar until I reached the top. And I said, well, this whole thing, whatever this whole thing is, I'm going to call it H bar L. Okay, okay. So I'm trying to find this top eigenvalue. And on the L square side, I know that doesn't matter which function I pick, can be the top, can be the bottom, can be any. This eigenvalue will be lambda. Okay. But I now wrote this L square like this. So I'm going to apply this L square on this top. So I have LZ square plus H bar LZ plus L minus L plus, all this acting on this F top. Well, but we know that L plus acting on the top is 0. So this term here disappears. Okay, and this is equal to this lambda that I'm trying to find. Okay. Now, using what I wrote here, I'm going to say that LZ square on F top is going to be H bar square L square. I don't know what this L square is, but we just is a symbol for the bond. Huh? Then H bar LZ will give me H bar square L. And this is lambda F top. So this means that lambda, now I found lambda. Lambda is H bar square L plus 1. Okay, so this is what this is. You see that this is the form that I just started the class today talking about. I showed to you that in the beginning of this chapter, we had the complicated equation involving theta, involving phi, blah, 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 which was equal when we were separating the equations by doing those separation of variables. The equation that was for theta and phi was equal to L plus 1, and those spherical harmonics. And we are seeing this L plus 1 showing up again as an eigenvalue of the L square, of the total angular momentum. So you see where we are heading towards. No? Remember what I said. We want to show to you that those spherical harmonics are the eigenfunctions of the L square. Okay, so, but I'll come back to this, I'll show to you. So for the moment, we found this. Okay, and this eigenvalue here, H bar square L plus 1, is the eigenvalue associated with L square. We're up to this point, we are not calling it the eigenfunction, we're not calling it spherical harmonics yet, we are just saying F. And if F is top, if F is bottom, if F is any F, the eigenvalue is always lambda, which is H bar square L plus 1. Okay. So we found that using the top one, but the bottom one will have the same eigenvalue and any F will have the same eigenvalue. Now let's go to the bottom one, playing with LZ. Okay, so we said that LZ on the bottom one is some eigenvalue that I do not know. And again, I'm going to use this trick. I'm going to say, well, I'm going to call it some L bar now. I don't know what it is. How did I arrive there? I had the eigenvalue me, and I was decreasing until I reached the bottom. And this is what I'm saying, that is H bar, L bar. Okay, so again, I'm going to use the trick that we did before. Remember that we introduced this L minus L plus, but instead of L minus L plus, since now I'm dealing with the bottom, the idea is, let's play with L plus L minus, okay? Very similar. Again, we go with the definition, so Lx plus ILy, product with Lx minus Ly. Here we'll have Lx squared plus Ly squared. We add the z and we subtract it. And then the cross products, not the x with the y, we have minus I Lx Ly, the commutator. Okay, so with this, we find that this L plus L minus is the L square minus the LZ square. And here we have I H bar LZ. I with I is minus, but there is a minus sign, so this becomes plus. Okay, so again, I found a new way to write the L square as LZ square minus H bar LZ, and that plus L minus. Again, I'm going to act on the bottom function. And I know that this has to be that lambda. I know that that lambda is H bar squared L plus 1. This doesn't change. Okay. But on this side here, what is it that we have? We have LZ squared minus H bar LZ plus L minus, all this acting on the bottom. As we said, L minus on that is 0. So what survives in this story? Remember, we wrote the eigenvalue with this form, H bar, L bar. So what I'm going to have here is H bar squared with L bar squared from the LZ. From the LZ squared, from the LZ, I have minus H bar squared L bar, and that's it. So then we found that this side here, I'm going to write as H bar squared L bar minus 1 is equal to that one, because that's the one that we said is always the same. Okay, so now we have a way to find what this L bar is. There are two possibilities for this equation to be true. One is if I put L bar equals to L plus 1, because this would give me L and this would give me L plus 1. This is a possibility. Another possibility that also works is if I say that this is minus L, okay? Because this will be minus L, and here I have minus L minus 1, and then I recover this part. Okay, so these are two possibilities that satisfy this equation. But this one cannot be. I'm saying that this L bar is associated with the bottom one. So the eigenvalue for the bottom one cannot be larger. L plus 1 cannot be larger than the eigenvalue for the top one. The eigenvalue for the top one was L. Okay? So this solution here does not make sense. So conclusion, this has to be the solution. So let me put these things together, okay? What we found out, the eigenvalue for the L square of this function is H bar squared L plus 1. Yeah, that's it. Now, we found that the eigenvalue for LZ for the bottom one, and your book just put B, okay? So I'll put it B also. Now we already convinced that this is the bottom. So the eigenvalue for this one is H bar minus L, okay? And the eigenvalue for the top one is H bar L. How do I go from here there? We go on applying the L plus. Yeah, so I start with the lowest eigenvalue that the LZ can have is this H bar minus L. If I apply the L plus, not that raising operator, I will have H bar minus L plus 1. If I apply again, H bar minus L plus 2, and we go on with this process until we reach H bar L. We've seen this before. We've seen this before when we were talking about the solutions of the spherical harmonics. This minus L plus 1, minus L plus 2, all the way to L is what we call M. Now we said the M, remember that we were talking about that periodicity, and then we found the solution in phi, and then we said, well, this M can be minus L plus 1, minus L plus 2, all the way, L minus 1 and L. Now so we have here 2 L plus 1 possibilities. And this came out now from the operator LZ. So I'm going to put all this together and say, the LZ acting on this function gives us an eigenvalue that is H bar M. What the value of this M will be depends on the function that we are dealing with, depends on L and M. And for the L square, again, this function depends, what we are going to get as an eigenvalue depends on the function that we are dealing with. And this eigenvalue is going to be H bar square L plus 1. So it depends on this L. So that's why we write this function with this index L and this sub and super index L and M. Well, what is that? Well, now we can rewrite these things in terms of the spherical harmonics. And I'm going to write to you the equations, okay? Just let me just... So the spherical harmonics are the eigenfunctions of the operator LZ and the operator, the operator L square. Okay, so these are the spherical harmonics. Okay, well, what we did in this whole procedure and what I expect you to know is we obtained the eigenvalues associated with these two operators. But the other part, which I'm going to show to you in the book, maybe in class I showed you the details, but now I'm just going to give to you as just equations without getting to it. Is the following. Let me get to this. Okay, so this is what we just showed, yeah. But what I want to show to you is, okay, now if we pick here, if we now write the LX, the LY, the LZ, the L square, all that in using now spherical coordinates, how would they look like? So this is what this section of the book is about. I'm just going to show to you how they look like, okay? You can go through this if you want, and I'm just going to show to you what they look like. This is the LZ, yeah? So you see the LZ acting on our function, yeah? So we would have LZ, the function, equal to H bar M and the function, yeah? Well, what is that? What this is telling us is that this is H bar over I derivative in phi. of this function. This is very similar to that equation that we solved when we started this chapter, which was that equation second order derivative in phi that gave us m, and well, at this point we are talking about this part of the wave function that depended only on phi. And we've said, well, the solution for this is that exponential I m phi. Well, again here, what is going to be the solution of this equation? That I m phi. Okay, so you see, if you put it in spherical coordinates, you go back to the equations that we dealt with in the beginning. Now let's have a look at the L square. The L square is this complicated thing. Yeah. Well, this is the equation that I told you when we started the class. This is this equation here. You see, this whole thing is the L square. This is the F, which is the spherical harmonics. This is the equation that we had in the beginning of the chapter. And remember, when we were doing that separation of variables, we said, okay, this left side is a constant, this right side is a constant, and we put this constant L plus 1. Why? Because this is, now we know, this is associated with the eigenvalues of the total operator L square. Okay. All right. So the other thing that I wanted to tell you that is on this, let me come back down, which is a problem I'm going to send to you to solve, but it's an interesting problem, is this problem 4.21. You will solve it as homework, but what is this? This is important. Let me remind you of something that we saw when we were talking about harmonic oscillator. We said, well, for the harmonic oscillator, it was long ago, no? We said A plus acting on some function, if I know this function, psi n, I will now get a new function, which is the psi n plus 1. I raise it. And here, there was a normalization factor. Nick is coming at the end. We have a normalization factor, which is the square root of n plus 1. And we did the same with the A minus, which gave us a new function, n minus 1. Remember that? Well, and then we said, okay, so if I know this, then this raised function is easy to get. This step up is easy to get. If I know the psi n, I just apply the A plus on the psi n and take this normalization factor into account. Okay, so this is something that we saw back in chapter 2. Well, now we are dealing again with raising and lowering operators. So if I have some function FLM, I can raise it by applying this L plus. So here I'm going to get the FLM plus 1. Well, this F, I'm writing F, but you know it's the spherical harmonics with some normalization factor. Okay? This is what this problem is about. And again, the same thing. If you apply the L minus, you're going to get it down. So M minus 1 with some normalization factor. So this problem is find this normalization factor. You see this? This is the normalization factor. And it's not as simple as it was in the harmonic oscillator, not just a simple square root. It's again a square root, but here it is. Now it involves L's and M's. Okay? But it's very useful because then we can find any other spherical harmonics if I know one of them. No? Can go on raising or lowering. All right, so this is, I'm just going to reach to just one more point here. So this is the point, up to this point is what I expect you to study for the test 3, now, which will be next week. I'm going to send you an email with the details, okay? But this is only up to this point, only up to this equation 4133. What is this equation 4133? So let me put everything together now. what were we trying to do since the beginning of this chapter? We were trying to find the wave function, the solution for the time-independent Schrödinger's equation. And we said, well, writing the spherical harmonics, it depends on r, theta, and phi. Okay, what are these eigenfunctions? Well, the eigenfunctions of what? They are the eigenfunction of the operator Hamiltonian. Okay, so this is what we are trying to find. Now, these functions, they are the eigenfunctions of the harmonic, of the Hamiltonian, but they are also eigenfunction of the L square part. How do I know that? Well, because this psi depends only on r, and then this L square ignores it, and the other part is the spherical harmonics. So this L square applied on this wave function is h bar L plus 1. So this the eigenfunction is also this eigenfunction, this psi, this eigenfunction of the Hamiltonian is also an eigenfunction of the total angular momentum. And if I play with LZ, I will see that it's also an eigenfunction, no? Because the LZ only cares about the part that depends, well, the solution depends on r, theta, and phi. The LZ depends only on the phi. The rest is just constants for it. No? So the wave function is also an eigenfunction of LZ with eigenvalue h bar m. So conclusion of that, the Hamiltonian, the total angular momentum, and the angular momentum in LZ, they are all compatible. They all commute. No? They all commute, and so therefore they all share the same eigenfunction, which is the solution of this time-independent Schrödinger's equation. Okay, and that's the end of the story for the test 3. Now what I'm going to start talking about is the last concept of this course, which is the concept of spin. But let's talk a little bit about that L. Now well, remember we said that the M was minus L plus 1 and so on, all the way to the final one, which is L. Now, so these were the eigenvalues of the LZ part, h bar m. Well, so we go step by step, raising this bottom one, the minus L. So I go minus L plus 1 plus 2 plus 3 plus n finally gives me the last one, L. So from here we conclude that this is the number of steps up, okay? So from here we conclude that this L is this number of steps divided by 2, which means if n is even, 4, 0, or 2, the L would be an integer. So what are the values that L can be? 0, 1, 2, 3, and this is what we were playing with before. We only saw the integer values of this L in what we were doing before. Now, if n is odd, then we get half integers. We would get half, 3 halves, 5 halves. Well, these ones we never saw. Okay? So when we are talking about the orbitals of this the electron, we never saw half integers. Where will these half integers show up? In the concept of spin. Okay? So what is spin? Again, let's start talking about classical mechanics. When we are talking about classical mechanics, let's pick something that is very familiar to us. Let's think about Earth turning around the sun. So here's Earth. Well, what do we know? That Earth has 2 kinds of angular momentum. One is the orbital. So the motion around the sun, but Earth also, so this is the motion of the center of mass, the orbital. But we also have what we call spin, which is Earth turning around itself and the spinning. Well, in classical mechanics, what we call spin is actually the angular momentum of each one of the entities that compose planet Earth. All the rocks, all the people, everything that is turning around. So it's the angular momentum of all these things. Now let's go to quantum mechanics. When we are talking about, for example, the electron orbiting around the proton in the hydrogen atom, well, we usually use this picture, but remember that we said this picture is not correct. Well, it's true that we can talk about the orbital angular momentum, and that's what we just talked about, the L's, the Lx, Ly, Lz. But we said, well, careful with this picture of the planetary system, because the electron is actually a cloud around that the proton. It's not just a little thing moving around. So we still have the angular momentum, the orbital angular momentum, fine. And we still have the spin. So we still have the two entities. The problem is trying now to understand or interpret the spin, because you cannot think about the electron orbit or turning around itself. The electron is something without structure. So what is this spin? It's not an easy thing to understand. It's some property that this particle, that this quantum particle has. It's some intrinsic property that this quantum particle has. It's like a tiny magnet that it belongs to this particle. How do we know that it exists? We apply a magnetic field and these particles react. Okay? Each particle has its own spin. So the angular momentum, the L, can change, depends if my electron is more or less excited. The angular momentum, the orbital angular momentum can change. The spin is fixed. Each particle has its own spin and it's not going to change. What are some examples? Well, if I think about electrons, protons, neutrons, quarks, leptons. So electron, neutron, protons are like the main constituents of matter, right? All of these particles, they have spin half. Okay? Well, the other particles, let's say photon, the photon has spin 1, graviton, which is the particle associated with gravity, spin 2, and so on. Okay, so each particle has its own spin. We are going to focus on the spin half, because this is the most common, or the first step in this story. And we are talking about the hydrogen atom, we are talking about electrons, we are talking about protons, so we are going to be dealing with the spin half. But you see that the spin can have integer values, the L, the 1, like the L had, 1, L1, 0, 1, 2, and so on. But the spin can also have the half integers one. So the ones that were missing before. Okay. All right. So as I said, we are going to be dealing with S half. And what are the possible values for the M? For the when S is half, the M is the same as we had before. The minimum value is minus S, so it's minus half. We increase it in steps, in integer steps, so the maximum value will be plus half. Okay, so this is what we'll be studying. And probably on Thursday in person, yeah? Okay, so how are we going to be dealing with spin? Everything that we learn for the angular momentum, Lx, Ly, and Z, we are going to just use the same procedure, the same formalism for the spin, for the Sx, Sy, Sz. The same thing that we learned for the angular momentum for the orbital angular momentum, we'll be using now for the spin. What does that mean? Commutator between Sx and Sy, we are not going to be deriving. We are just going to be using that they do not commute, and it should be IH bar and SZ. And the same thing for Sy, SC, and the SZ, SX. Will be IH bar, and the next one, IH bar, and the next one, following that cyclic procedure. We are also going to be talking about, as we did before, the total angular momentum. Oh, the total now spin. Angular momentum was what we did before, now for the spin. Okay, so it's again the same formalism, nothing has changed. Okay, all right, so again we select 2. Now the S square commutes with SX, commutes with SY, commutes with SZ. Again, we are going to pick the 2. We are going to pick S square, the total, and the SZ. And we are going to be looking at their eigenstates. The eigenstate, we are going to call it SM. SM. Remember, when we are using the angular momentum, not the orbital angular momentum, we have those solutions LM. These were the eigenfunctions that depend on L and M. Here again, it depends on S and M. Okay. What are the eigenvalues? Just follow what we learned before. H bar square. Now, instead of L, I'm going to be dealing with S, and it's going to be S plus 1. Okay, so we are just following, we are not deriving anything. How about the eigenvalue for SZ? It will be H bar M, just as we had before. And this is the eigenfunction. Okay, so that's where we are starting from. Okay. All right. And we are going to start from this for each case of S, for each particular spin kind. As I said, our case will be spin half, which means there are only 2 possible solutions. There are 2 possible eigenstates. So we have the eigenstate when S is half and M is minus half. Or we have the solution when S is half and M is plus half. Okay? So again, I repeat, when S is half, M can be the lowest value is minus S, so it's minus half. I go on increasing step by step 1, while in this case, there is only one possibility, half. Okay, so these are the 2 possible eigenstates of S square and SZ, the 2 eigenstates of this operator. So what we're going to be doing is, and that's how I'm going to start the next class, I'm going to start playing with some notation. And I'll say the following. Well, this state, half and plus half, this eigenstate means a spin that is pointing up in the Z direction. In the Z direction because it's an eigenstate of the SZ. So it's a spin that is pointing up in the Z direction. And I'm going to be using a notation for that will be very convenient. This is chi. This is a Greek letter called chi. But I'll say that the chi plus, which indicates this spin pointing up, is a vector 1, 0. Okay. The other state, the half with M being minus half, means a spin that is pointing down in the Z direction. And I call this state, this chi minus, which is this vector 0, 1. Okay. So that's what we're going to be starting from whenever, next class, but whenever we are trying to describe a spin half, like an electron, a proton, a neutron, we can use these two states, these two vectors as the basis vectors. So any general state of our spin half, any general state, I'm going to call it chi, will be a linear superposition of those two vectors, of those two basis vectors. So any state of this spin, of this particle, can be written in general like this, which means A of the vector 1, 0, the spin up, and B of the vector 0, 1, which is the spin down. So what we have is a general state for this spin half is this vector A, B, which means the state of this spin is a superposition, no? It's a linear combination of two possibilities. What we are saying here is that this spin is not just pointing up, it's not just pointing down, it's a superposition of up and down. Okay? If I measure the spin, it will collapse. If I measure the z component of the spin, it will collapse. And then it will collapse either on the up case or on the down case. It will have absolute value of h, absolute value of a, absolute value of a square, chance of collapsing to the up case. Absolute value of b square, chance, probability to collapse on the down case. Okay, well, I think that's good. It's good enough. I'm going to start again next class at this point, and this will be in person. Now let me stop recording. Okay.